A warm welcome to all my dear students. So we are continuing where we left off in the previous lecture. The previous lecture we were dealing with certain optical phenomena related to light, where light traveling in one medium goes into a light traveling in one transparent medium goes to another transparent medium, a different transparent medium, and we saw what happens to the ray of light as it travels from one type of transparent medium to another type of transparent medium. And this physical process that happens to the light between at the interface of two medium was called the refraction. Also, refraction explains a lot of optical phenomena in nature. So we need to study refraction in a more detailed manner, and in this lecture we will be dealing with the quantitative study of refraction using a physical quantity known as the refractive index. This is a number, it's a ratio. It's a ratio, by the way. It has no dimensions. It is just a ratio, not a ration, it's a ratio. I'm so sorry. It's a ratio. It has no dimensions. It has no unit. It is just a number. Unitless. It is unitless. So let us see how we define refractive index. How one defines refractive index and how refractive index can be used to explain or predict refraction. So let us move on to the detailed study of what refractive index is. So before going to refractive index, let me just warm you up of the previous session. What refraction was, suppose there is an interface. This red line is an interface which separates two transparent medium. Suppose this was some medium 1 and this was some medium 2. Below the red line, it is actually, this red line is in fact a surface, and we are see it looks to be a line only because you are viewing it from a sideways direction. So it is not a line, in fact it is a surface, and it appears to be a line, and it is an interface. It is the boundary between two medium 1 and medium 2. What happens at the interface is the matter of interest. In any given medium, in any given transparent medium which is uniform in its optical density, the light ray is a straightest possible path, and at the interface between these two medium is what the magical thing happens. The light at the point of incidence, if we draw a certain normal at the point of incidence, which is just an imaginary line. Remember, this is just a reference line. It is imaginary. It is totally imaginary. It does not exist, and normal is always perpendicular to the plane of interface, the interface plane, and the incident ray at the point of incident, when it enters the second medium, what happens? Either the ray either the ray. See, the ray does not move in a straight, it moves in a straight line, but it does not follows the same path, but instead it makes a smaller angle to with respect to the normal, or the angle between the normal and the ray in the second medium is larger as compared to the outer side. See, this angle, the angle the angle over here, this angle, this particular angle is known as the angle of incidence, and this angle in the second medium between this ray known as the refracted ray and the normal is known as the angle of refraction. It appears that due to refraction, angle of incidence will not be equal to the angle of refraction. So there is a deviation, of course. There is always, of course, a deviation in the path of light. So this was the phenomenon of refraction. And also we learned a law known as the Snell's law. We learned this famous law which goes by the name Snell's law. Snell's law which goes by the name of Snell's law. Snell's law, which stated that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. So the deviation occurs which obeys this law. The deviation occurs in such a manner which obeys this law. What did I mean by deviation? The deviation means when there is an interface and when this incident ray moves from one medium to another medium, anytime this angle I and this angle R must obey Snell's law. Must obey Snell's law. So it means that if you are independent to change this angle of incidence, you can change the angle of incidence, right? You can put your torch over here. You can put your torch over here, or you can, if you want, you can put your torch here, or here, or even here, or even here. So you can move your torch at any angle, but the refractive angle, the refracted ray, will only select those paths, will move through those paths which is in accordance with the Snell's law. Because according to this equation, as you can see, this equation, in this equation you can see that sine R changes is related to sine I through this equation. This is the Snell's law. This is the Snell's law. So you cannot independently change R. Only independent quantity that can be changed is the angle of incidence. So Snell's law and refraction makes things very interesting. Now let us move on to defining what refractive index was. So refractive index is a physical is a number, is a refractive index is a number. It's a physical quantity which dictates the optical density of a material. So it By looking at the refractive index, you can know what will happen or how the deviation of the ray could occur. If you want to predict what happens to the ray of light as it enters from one medium to another, whether the ray bends towards the normal or whether it moves away from the normal, if you want to predict this, you need to know the refractive index of both the medium. So now one more thing is apparent, that refractive index is a is some physical quantity which is associated with each medium. You can define refractive index for medium 1. Similarly, you can define refractive index for medium 2. So it is the property of the medium itself which is used to define refractive index. Now how do you define, suppose if you have medium 1, you want to define the refractive index of medium 1. How do you do that? It's very easy. You take medium 1, you slice out a piece of medium 1. So see, this is a piece of medium 1, okay? Now you place it in vacuum. So everywhere around this medium 1 there is vacuum, okay? So this acts as an interface. This acts as an interface. So this is an interface below which is medium 1 and above it is vacuum, which itself is a transparent medium where through light travels at the fastest possible speed. So in vacuum, the speed of light is c, is denoted by c. C refers to celeritas, as you know it. Celeritas. And the value of c in vacuum was almost 3 lakh. I'm sorry, excuse me. My styluses go wild and crazy sometimes, I don't know why, what's wrong. It's actually a custom homemade stylus. So 3 lakh kilometers per second. So that is the speed of light in vacuum. And suppose a ray of light traveling at that speed is moving towards the interface from vacuum. See, let me use another color so that you don't get much confused about it. Oops, I missed that. So let me just reduce the size of this eraser. Okay, thank you. Okay, so we have another color. I would use the yellow instead. Okay, suppose we have a ray of light like this, and it was moving in vacuum and it hit the interface at an angle with respect to the normal, say I. Here the speed is c. As mentioned before. Now as it enters the second medium, what happens? It moves at another speed. Since c is the fastest possible speed at which light can travel, in any other medium other than vacuum, the speed of light will always be lower than c. So suppose medium 1 in medium 1 the light travels at a speed v1. Now we can use these two speed velocities, the value of these velocities, to define refractive index. So refractive index is nothing but the ratio of velocities. So it goes like this. You have refractive index of medium 1 with respect to vacuum. So this is what means. See, refractive index, the symbol for refractive index is in mostly used symbol is the uh, alphabet small lowercase alphabet n, or in higher textbooks the refractive index is denoted using the symbol mu. It's mu. If you have not studied this is a Greek letter, and refractive index is denoted either using n or mu. Mu was actually a predated version of the refractive index. Most recently it is n which is used. There is no restriction on which symbol to be used, but for NCERT syllabus, according to the NCERT syllabus, you are supposed to use n. So coming back to the definition, you have let me use some other color, maybe green. Yeah, refractive index of the medium 1 with respect to the vacuum is defined as velocity of light in vacuum divided by velocity of light in medium 1. So remember this definition. This is one important definition in the whole physics. This is how you define refractive index of any given material. So it is this ratio of the velocities of light in vacuum and in that medium. So in words, this would look like refractive index of a material is nothing but the ratio of speed of light in vacuum. Actually, the spelling of vacuum should be CCUM, not CUUM. Okay, so that's a mistake. Let me just correct it. It's always a confusing topic. I've heard people use that differently. CCUM, that's vacuum. Speed of light in vacuum divided by speed of light in the medium. So whichever medium you are using and whichever medium you want to quantify the refractive index of, you do this ratio, that's all. So also this particular quantity, this refractive index is just, you do not use n1v, but instead you can just say call it refractive index n subscript 1, which only means that it is the refractive index of medium 1. This ratio, this refractive index is also known as the absolute refractive index. Why is it called absolute refractive index? Because it is the refractive index of the medium with respect to vacuum. Now, what what would happen if that is the case? How could you then define refractive index between two medium? You can see, suppose medium 1 has refractive index say n1, and you have another medium which has a refractive index known as which is n2. You have two transparent mediums, and one medium has refractive index n1, another refractive medium with refractive index n2, and suppose light enters in this manner from medium 1 to medium 2, and let me just draw the normal so that we could indicate the angle of incidence. And as it enters from medium 1 to medium 2, the beam of light suffers a certain refraction, certain deviation, and this angle in the second medium is known as angle of refraction. In medium 1, the ray has a velocity v1. In medium 2, the ray has velocity v2. Using v1 and v2 between two mediums, I am going to define a new quantity, not a new quantity but a different one, but it is refractive index itself, and that quantity is known as relative refractive index. So you previously studied refractive index, and which was called the absolute refractive index, and absolute refractive index is what is referred to as the refractive index of the medium. Now what is relative refractive index? Relative refractive index is the refractive index of one material. Say, if you want to define the relative refractive index of medium 2 with respect to medium 1, how do you define that? All you do is you take the ratio of the velocity of light in medium 1 divided by velocity of light in medium 2. So this is the relative refractive index of medium 2 with respect to medium 1. So this is how you define relative refractive index. So you might even think that you can define refractive index of medium 1 with respect to medium 2. So what is the refractive index? What is the refractive index or the relative refractive index of medium 1 with respect to medium 2? It's nothing but n 1 2. See, these are subscripts. Okay, you will write n and then you will write 1 2 on the subscript of as a subscript to n. So it is the velocity of light in medium 2 divided by velocity of light in medium 1. So that is the relative refractive index of medium 1 with respect to medium 2. So you can see the difference. See, if you want to what was the relative refractive index of medium 1 to medium 2? It was n 1 2, and it was given by v2 over V1. And what was relative refractive index of the medium 2 with respect to medium 1? It was V1 over V2. And how is N12 and N21 related? Can you guess? Yeah, exactly. N12 and N21 are actually reciprocals of one another. See over here in this equation, if you take the reciprocal, it will become V1 by V2 and the LHS will become 1 over N12. This will become V1. If you take the reciprocal here, it will become V1 by V2 and this side will become 1 over N12. And what is V1 by V2? It is nothing but N21. So you get this relation also. N21 is equal to 1 over N12. So this is the reciprocal relation. So you learn two things today. Now, and those two things were the absolute refractive index and the relative refractive index. So how do you make use of it? How do you make use of it? If suppose one medium has a refractive index N1, another medium has a refractive index N2. What you do is you check whether N1 is greater than N2 or not. If N1 is greater than N2, which means the light ray is moving slower here, and if N2 is less than N1, then it is moving faster in the second medium. So what happens? The angle of refraction will be more if N1 is greater than N2, which means angle of incidence will be less than angle of refraction, provided you have placed the mediums in such a manner where angle of incidence is in medium 1 and angle of refraction is in medium 2. So you just have to check the ratio N12 was N2 over V2 over V1. And how do you define N1? Absolute refractive index N1 is actually nothing but C over V1. And how do you define N2? N2 is C over V2. So this is how you define absolute and relative refractive index. Using relative refractive index, you can understand whether the beam of light will bend towards, or bend away from the normal. Because if the light moves faster in medium 1, if the light ray moves faster with respect to medium 2, then light ray will slow down and it will bend towards. So in this case the light ray is slow, or medium 2 has higher optical density. If higher optical density can be known by looking at its refractive index, so higher refractive index implies higher optical density, and if it is faster in second medium, it will bend away from the normal. So let me stop the video here. You could go through the video several number of times, learn it more clearly, and if any doubt persists, we will be discussing it through our online platform. Thank you for watching. We'll meet you in the next lecture session.